We're going to prove in this video that there are infinitely many prime numbers. It may have first been proved by Euclid in the year 300 BC. So this proof, or one very similar to the one that we're going to do, was Euclid's proof, and it has been around now for 2,000 years, and the kind of reasoning is still one that is very understandable to us. So I hope you enjoy this. Before we start, I just wanted to mention that it was just last year that Professor Curtis Cooper from the University of Central Missouri discovered another prime number. And you guys will really know how big this is because you were shocked to find out how big 2 to the 50th was when we talked about stacking the paper, or how much money was on the checkerboard after doubling 63 times. Well, this latest prime number is 2 to the 57,885,161 power minus 1. It has 17 million digits. So they just keep coming. And people keep searching, mathematicians keep searching using supercomputers to find another prime number. If you're interested in this, you could read more at this link that I have here for you. So before we begin the proof that there are infinitely many, let's remind ourselves of exactly what is a prime number, what is the definition. So we learned in class that a prime number is a natural number greater than 1. In other words, 1 is not a prime. A prime number is a natural number greater than 1 that is only divisible by 1 and itself. We wrote down some prime numbers in class. 1 is not a prime. 2 is the first prime, the smallest prime, and the only even prime. And then we have 3, 5, 7, 11, 13, 17, 19, 23, and you can keep going. Just count 24, 25, 26, 27, 28, 29, and 31 has no divisors, 32, 33, 34, 35, 36, 37. No, 37 has no divisors, and so on. It gets a little bit harder as you get up there to know if it's a prime or not, but you can always look online and find lists of thousands of them if you want to. But those are the first few. Those are numbers that have no divisors other than 1 and themselves. So, what could you say about a number, a prime number, p, let's call it p, any prime? What could you say happens if you divide it by some other number? Not with your calculator, but let's say you do long division. Let's see. 17 is a prime. So just remember from elementary school, if we divided it by, say, 5. Okay, so we'd get 3. And then we would get a remainder of 2. So we could say that 17 is 5 times 3 plus a remainder of 2. And if a prime number then is divided by some other number, any other number other than itself and 1, you're going to get a remainder. And that's what I wanted you to see. You'll always get a remainder unless that divisor is itself or 1. The division algorithm is a theorem that tells us what we just said more formally. If a number m is evenly divisible by a number d, then m is the product of d and some other number I called q, like for quotient. For example, you know 15 is divisible by 3, so we can say that 15 is equal to 3 times some other number, which would be 5 in this case. Or 30 is divisible by 6. That means that 30 is 6 times some other number, 5. Or 100 is divisible by 2 because it is equal to 2 times 50. If a number is divisible by d, then it is equal to dq for some number q. And you don't need to memorize this, but try to see how we write it in a formal way like this. Now, if a number m is not evenly divisible by d, then when you divide by d, you get a remainder. So we say right here, this is how you say that mathematically. If it is not divisible by d, then it is equal to dq plus some remainder. And you can always make the remainder less than the divisor. For example, we said 17 was not divisible by 3. Well, 17, if I divide it by 3, I get 3 times 5. I get it 5 plus a remainder of 2. Now, of course, you could say that 17 is equal to 2 times 5 plus a remainder of 7, but this is not how we wrote it here. We usually would choose to make the remainder as small as possible. So we would write 17 is equal to 3 times 5 plus 2. Remember, this is called the division algorithm, and it is a truth in mathematics that whenever you have two numbers, and let's just say d is smaller than m, you can write m equals dq plus r, where r is a remainder of 0 if it goes in evenly, but if not, r is a number between 0 and the divisor. So we haven't started proving anything yet, but these are things that you need to know in order to follow Euclid's proof. Can you name a number that when divided by 3 leaves a remainder of 1? Well, put it on pause and come up with one yourself. But it's, of course, pretty easy. Let's see, a number, well, 31 is equal to 3 times 10 plus a remainder of 1. Or you might have said 4 is equal to 3 times 1 plus 1. In both cases, a remainder of 1. Now, how about the next one? Put it on pause and read the question and see if you can find it. How about a number that when divided by 2, 3, 4, and 5 leaves a remainder of 1? Well, put it on pause and see if you can find one. And then come back and look at this one. It's got to be 2 times something plus 1. It has to be 3 times something plus 1. It has to have a factor of 4. Well, not a factor, but when you divide by 4, it leaves a remainder of 1. And when you divide by 5, it has to leave a remainder of 1. And then this. This is an example of a number that leaves a remainder of 1 when you divide it by 2, 3, 4, or 5. Now, there's many, many more. This is just a simple way of making one up. Notice we could write this number as 2 times 60 plus 1. We could write it as 3 times 40 plus 1. We could write it as 4 times 6 times 5, 30 plus 1. Or we could write it as 5 times 24 plus 1. I think I did all that right. But we can write it as 2 times something plus 1, 3 times something plus 1, 4 times something plus 1. And there's no need to write all these out here. I did it just this once to show you that each one can be written like we did up there. So just write 2 times 3 times 4 times 5 and add 1, and that gives you a number that we were looking for. Now, how about a number that when divided by all numbers less than 10 leaves a remainder of 1? All numbers except for 1, of course. So put it on pause and see if you can come up with a number. Okay, well, hopefully you came up with this number. You could have 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 plus 1. Multiply all these together and add 1. Some of you may have seen this as 10 factorial plus 1. If you haven't, that's fine. You don't have to think of it as 10 factorial. Notice any one of these numbers could be taken out, like 7 times all the rest plus 1. So it's not divisible by 7, it leaves a remainder of 1. Another way to write this that you'll see a lot in our class, instead of having to write out all those numbers, 2 times 3 times 4 times dot dot dot, as soon as you can see that we're just going up by 1 here, 2 times 3 times 4, and then dot 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 times 10 plus 1. And of course, you don't need these, but what we're thinking is multiply these numbers together and add 1. Now that number, whatever it may be, it's a big one, and I don't care what its numerical value is, but I do know that it is a pretty big number that is not divisible by 2, 3, 4, in fact not divisible by any number, any natural number less than 10, except for, of course, 1. And we're going to look at one more example before we start the proof. Notice I've used x's here for multiplication. You'll see both. Here we have v, a number that is 1 times 2 times 3 times 4 times 5, all the way up to and including the factor 91. Take that huge product, 91 factorial it is, and add 1. What numbers do you know for sure do not divide v? Well, you know that 2 doesn't, 3 doesn't, and now hopefully you're reading this notation here to mean that neither does 4, 5, 6, 7, or any number up to and including 90, 91. None of those numbers divide evenly into v because they all leave a remainder of 1. Does this mean that v has no divisors at all? Does it mean that v is a prime number? Now, if you don't get this answer, you have to stop and write down some examples for yourself and multiply them out, not one this big, but multiply them out and see that this does not mean that v is prime. All it means is that it is not divisible by any numbers less than or equal to 91. It may be divisible by 1,206, I don't know. Well, it won't be divisible by that because it's not divisible by 2, but maybe it's divisible by 101 or 1,000, I don't know, 1,003, I'm not sure. But it could be divisible, and it probably is divisible by other numbers, just not 1 through 91. Another example to show you that, I think I should. Let's take the number 1 times 2 times 3 times 4 times 5 and add 1. Now, if we call that number something m, we know that number is not divisible by 2, 3, 4, or 5. But let's see what the number is. Let's see, that's 6 times 20. So 6 times what's 121 after I add the 1. Oh, well 121 is divisible by 11. It's divisible evenly by 11. 121 is 11 squared. So keep in mind, we are not saying up here with this long, much bigger number, we're not saying that it is a prime number. We're just saying that if you divide it by any number between 1 and 91, that you will get a remainder of 1. Therefore, it is not divisible by any of those numbers. It might well be divisible by numbers greater than 91. Well, you can see how important it is to understand this logic, because we still haven't started the proof. I have one more example. If capital M stands for the number 5 million factorial, 1 times 2 times 3 times 4 times all the way up to 5 million, and you add 1, what numbers do you know for sure do not divide that thing? Now, your calculators could not calculate that number exactly and give you the digits. It's huge. But we do know that it is not divisible by any number up to and including 5 million. Most likely it is divisible by numbers greater than 5 million. We have no reason to believe that it would be a prime number. So let's generalize for S. This number here. This is the first example that I'm saying in general. S is a number that is n factorial. In other words, the product of n with all numbers smaller than it, all the way down to 1. Multiply all those together and add 1. What do you know about this number? You do not know that it is a prime, but you do know that S leaves a remainder of 1 when divided by any number less than or equal to n and greater than 1. Of course, we're not talking about 1 itself. 1 divides everything. You could leave this factor in here, or you could just take it out. It doesn't matter. It's not divisible by 2, 3, 4, 5, 6, or anything up to n. It very well may not be prime, though. If it is, let's write another note here, because this is the important thing for you to see. That's why I did all these examples. S is not necessarily, it may be, depending on n, necessarily a prime number. But we do know, but if a number divides S, we know it is greater than n. That's what we know about it. It has to be greater than n. So make sure all of the last 4 slides have been saying the exact same thing. Please make sure that you understand this deeply before you go on to the proof. So I'll put it on pause again and make sure you go back and make sure that you understand what we've been talking about. It's just really one concept. Okay, so now we'll do the proof that there are infinitely many primes. We start by supposing not. We are making a supposition that there are not infinitely many prime numbers. So we have to then say, well, whoops. Okay, so if there are not infinitely many prime numbers, let's write down some consequences of that supposition. If there are not infinitely many, then Oh, sorry about that. Then there is a finite. Learn to use these words. A finite number of primes. Well then, if there is a finite number of them, there's a biggest one. So there is a biggest prime. And let's give it a name because we're going to use it. Capital P. So from now on, capital P stands for the biggest prime. Because we have supposed that there are not infinitely many primes, there must be a biggest one. And what I'm hoping will happen in the proof is that we will come up with a contradiction to something that we know is true in mathematics, and therefore we'll go back and say, whoops, that supposition was wrong. And therefore there would be infinitely many. So we're going on the supposition that there's a finite number of primes and thus a biggest prime, and we're calling it capital P. All right, so again, if there is a finite number of primes, there must be a biggest prime, capital P. So we are going to make a huge number. Huge, because we already know at the first slide of this, I told you there was a prime that had 77 million digits in it. So this capital P is bigger than anything we can imagine, but it's the last one. It's the biggest. And we're going to look at a number larger than we can even imagine. M, we're making this number, M, is the product of P and all the numbers smaller than it. 1 times 2 times 3 times 4 times 5, all the way up to P, and then after we multiply all those numbers together, we're adding 1. Now, from what we did in the first few slides, you know then that M is not divisible by any number less than or equal to P, except for 1. M is not divisible by any number less than or equal to P. Well, put it on pause and see if you can think by yourself of why then capital M is not divisible by any prime number. Hopefully you came to the decision that it is not divisible by any prime number because all primes, and I'm going to put in parentheses, by our supposition, what we assumed at the beginning of the proof, are less than or equal to P. So we have made a number here. If there's a biggest prime, we have just created a number, a really big number, that is not divisible by any prime number at all. So if M is not divisible by any prime number at all, what kind of a number is M? It has no prime factors. No prime factors. So what kind of number would M be? And I bet you got it. M would have to be a prime. But that's impossible. Can you remember why it's impossible? M was equal to 1 times 2 times 3 times 4 times all the way up to P and adding 1. M is much bigger than P. And P was the biggest prime. And P was supposed to be the biggest prime. What we've done here is show that if there was a biggest prime, we could make one bigger, which makes no sense at all. So our assumption that there are finitely many primes is incorrect. And we can conclude that there are infinitely many primes. The way that I did this in the video is called a proof by contradiction. You start your proof by assuming that what you want to prove true is indeed not true. And on the assumption that it is not true, you deduce by logical reasoning a contradiction to a known fact. Here we contradicted our very assumption that P was the largest prime. So therefore the assumption has to be wrong, and we can conclude that that what we wanted to prove true is indeed true, because if it were false, it leads to a contradiction.